we'll start some important problem which is basically given in different competitive examination and graduation course. So we'll start from problem number 3. So here our question 3 is basically let a relation row on a set Z, that means set of all integers, by A row B if and only if AB is strictly greater than 0 for all AB belongs to Z. And the question is examine if the relation is reflexive, symmetric and transitive. So that means this relation is reflexive or not, symmetric or not, or transitive or not. Now first we will check this relation is reflexive or not. So before that you will write given relation row on the set Z by A is related to B if and only product of AB, this is strictly greater than 0, that means positive, for all AB belongs to Z. So this is relation. That means A is related to B if the product is greater than 0. And again the product of greater than 0, then we can say A is related to B. Now we will examine if is reflexive or not. So what we will take for reflexive? Let we take any arbitrary integers. Now then if we multiply A with A, that will be square. And that we can't say it is strictly greater than 0, we can say it is greater than equals to 0. Okay. So we can't conclude here A into A, this is strictly greater than 0. Why? Because if we take A greater than 0, so in general, here our comment is, in general, A square is not greater than 0, strictly greater than 0, for all A belongs to Z. Why? Because if we take A equals to 0, that integer, and in this case what is happened? A multiple A, that means 0 multiple 0, it is exactly 0. So that means here for A equals to 0, that integer A is not related to A. And we can conclude here row is not reflexive on Z. Now we come to second part, that means it is symmetric or not. How we will prove it is symmetric? So for this part, what we will check? We will check let A comma B belongs to Z be such that A is related to B, that holds. So now for symmetric, what we will prove? A row B, that implies B row A. So what is meant by A row B? That is basically the product of these two number greater than 0, two integer, because A row B if and only if AB greater than 0. So, and what is B row A? This means BA greater than 0. Now we can write here AB greater than 0, since if XY belongs to Z and the product of two integer is strictly greater than 0, that must imply YX is greater than 0. As XY equals to YX for all XY belongs to Z. So with respect to multiplication, it is basically commutes. Two integer are commutes. So obviously what we proved? What we proved? We proved here A row B implies B row A. We have taken AB as arbitrary. So what we conclude? A row B implies B is related to A for all AB belongs to Z, and hence we can say row is symmetric on Z. Symmetric on Z. Now we come to the third part. We will examine row is transitive or not. So what we will do? We will take 3. We just check here it is transitive or not. Let ABC belongs to Z be such that A row B and B row C holds. So what we have to prove? So then from if it is transitive, then A row B and B row C, that implies A row C. That we need to prove. Okay, so we'll continue now. A row B, that means AB is greater than 0. And B row C, that means BC, that product is greater than 0. So from that we can write, but what if it is A row C, you need to show AC greater than 0. So now AB greater than 0, BC greater than 0, that means AB multiple BC greater than 0. And since you know x greater than 0, y greater than 0, that implies xy must be greater than 0. So from that we can write A B squared C must be greater than 0. So and in that case we can write AC greater than 0. Why? From that we can write AC greater than 0. Since A row B, that implies AB greater than 0. Oh, that means either A greater than 0, B greater than 0 both, or A less than 0, B less than 0. And from that we must conclude if you take either B greater than 0 or B less than 0, in both cases B square must be greater than 0. So that means AC must be greater than 0, so A row C holds. So what we get here? A row B and B is related to C. That implies A is related to C. So here A, B, C are arbitrary. So therefore A row B and B row C, that implies A row C for all A, B, C belongs to Z. So thus we conclude that row is transitive on the set of integers. So what we get? Our conclusion is here. The row is symmetric and transitive, but it is not reflexive on Z. So this question you may have asked in as a MCQ type question. Let row be a relation on Z be defined by is related to B if and only if AB greater than 0 for all AB belongs to Z. Then which of the following are true? Option A, row is reflexive, symmetric, but not transitive. Next, option B, row is symmetric, transitive, but not reflexive. Option C, row is transitive, reflexive, but not symmetric. And option D, rho is an equivalence relation. Equivalence relation on Z. That means reflexive, symmetric and transitive. So what we have seen here, we have seen it is reflexive, it is not reflexive, but it is symmetric and transitive. So option B is correct. All other options are false. Now we come to the next important question. The question is a similar question. This question is also important. State true or false with justification. With justification. On the set of integers, on the set Z of all integers, a relation rho is defined by a rho b if and only if product AB is greater than equals to 0. Previously it was greater than, strictly greater than 0. Now a rho b if and only if AB greater than 0, where AB belongs to Z. Now then rho is reflexive and transitive. Rho is reflexive and transitive. So you need to show this statement, the whole statement is true or false, but we need justification. Okay. So solution will give the comment. It may be true, may be false, we don't know, but we'll move to the justification. So we'll check first it is reflexive or transitive or not. Then we'll say the answer. It will be true or false. Okay. Now this part will be pending. We'll continue the justification. After that, we'll write the answer. Okay. So if we check the reflexive property for reflexive, what we will do, we will take let A belongs to Z. We don't need to reflexive or not, we will check A belongs to Z. So then A multiple A, that means A square. The square of a real number, in fact an integer, always greater than equals to 0. So that means A rho A holds. Here A belongs to Z is arbitrary, so we can conclude A rho A holds for all A belongs to Z. Here, since x square is greater than equals to 0, for all x belongs to R, that result we know. So here we can conclude rho is reflexive. Our conclusion is rho is reflexive on Z. Now we think about the transitive. So next we will check our claim rho is transitive on Z. Rho is transitive on Z. That we need to prove. So what we will take, let A, B, C belongs to Z be such that A rho B and B rho C holds. So then from A related to B and B related to C, we need to show for transitivity A related to C. So what exactly the meaning of A related to B and B related to C? A related to B, that means the product of these two integers greater than equals to 0. And B related to C, that means this product is greater than. What exactly means A related to C? This product is greater than equals to 0. So we need to show AB greater than 0 and BC greater than 0. From that relation, we need to show AC greater than 0. So we know if x greater than equals to 0, y greater than equals to 0, then the product must be greater than equals to 0. So that means AB multiple BC, that is greater than equals to 0. So that means A B square C greater than equals to 0. Now you know if B is basically integer, and from that we can write B square must be greater than equals to 0. So that means here AC must be greater than equals to 0. So A row C holds. So therefore A row B and B row C, that implies A row C. Since ABC arbitrary, so A row B and B row C, that implies A row C for all ABC belongs to Z. That means our conclusion is rho is transitive on Z. So what we checked? We checked it is reflexive and as well as transitive. So this is proved. So that means the statement is true and this is the justification. So why it is reflexive and transitive, that we have done. So you will check, this is your homework. So this relation is symmetric or not? Yes, obviously it is a symmetric relation. That means it is an equivalence relation. But in position of AB greater than equal 0, if we take AB strictly greater than 0, so reflexive relation will not hold. So on that case, it will be not an equivalence relation. Now we come to the next important problem. What is the problem? Next problem is, next question. Determine the nature of the following relation. The nature of the following relation. Rho on Z. What is the relation? Rho equals to all those ordered pair AB belongs to S cross S. Where S is basically set of all positive integer S cross S such that mod of Z is basically S here. Such that mod of A minus B, that means distance between A and B are less than equals to 3. So nature means we will check it is reflexive or symmetric or transitive. So we just examine if it is reflexive or not, or symmetric or not, or transitive or not. How will check? Or your question may be, examine if rho is reflexive, symmetric and transitive on Z or not. So how to solve this kind of problem? So for reflexive, you will first let A belongs to Z. Then what will be the distance of A from A? So this distance must be 0. That we can say less than equals to 3. So that means A row A holds. So therefore, since A is arbitrary, so A row A holds for all A belongs to Z. And hence we conclude rho is reflexive on Z. Now we'll check symmetric. It is symmetric or not. So for checking symmetry, we will consider let AB belongs to Z be such that A row B holds. So then what we will prove? From A row B, we need to show B row A. So how will show from A row B to B row A? So what is the meaning of A row B? That means the distance between AB is less than equals to 3. What is the meaning of B row A? That means B minus A, that distance is less than equals to 3. And from A minus B, that modulus must be equal to mod of B minus A. And since mod of X equals to minus of mod X for all X belongs to R, that we know. So obviously A minus B less than equals to 3. That means distance between these 2 points AB, if the distance is 3, So obviously the distance between from B to A is also 3. So what we get? So therefore we get A row B implies B row A for all AB belongs to Z, and hence we conclude rho is symmetric on Z. Now we come to next important problem. So next important features, that means it is transitive or not. Now you just think, if A and B, that distance is 3 unit, and B distance C, if you take A here, B here, and C here, that is also 3 unit. So maybe the distance of AC may be less than, not maybe less than or maybe greater than. If we think about, okay, this is your C, that is 3 unit. A here, B here, and C here. So this is 3 unit, this is also 3 unit, this is A, this is B, this is C. So why AC, that distance will be 3? That may not be possible. So now we'll think about some example. So just you will take, let A equals to 1, B equals to say 3, and C equals to 5. All are integer. So then you know A minus B, that means 1 minus 3, this is equals to 2. And that is less than equal to 3. B minus C, this is 3 minus 5, this is 2, this is also less than equals to 3. Okay. So that means A row B holds and B row C. That is, I am saying 1 row 3 holds and 3 row 5 holds. But what about A minus C distance? That means 1 minus 5, this is 4. This is not less than equals to 3. So that means A is not related to C. That means 1 is not related to 5. So what we have seen? So we have seen it is not transitive. So our conclusion is rho is not transitive on Z. Okay. So thus our conclusion, rho is reflexive, symmetric, but not transitive on Z. Okay. Now next question, similar kind of question, maybe you have asked in your examination. Examine if, so this is question number 3, this is question number 4, again we move to question number 5. Now you have given question number 6. So examine if the relation rho on the set S, here S means the set of all integers is one reflexive, 2 symmetric, and 3 you will check transitive. So what is the relation? The relation is examine if where rho is defined on Z by A row B if and only if A minus B is strictly less than 3. where AB belongs to Z. We need to check it is reflexive, symmetric or transitive or not. So first we will come to the reflexive relation. 1. So that means A row A holds or not. So we will take let A belongs to Z. Then A minus A, that means 0. It is obviously less than 3. That implies A row A holds. So A row A for all A belongs to Z. So that means row is reflexive on Z. Now we come to the symmetric. So what we will take? Let A comma B belongs to Z. Then with A row B holds. So now A row B, that means A minus B is less than 3. But that does not mean B minus A, this is less than 3. This may not happen. Why this is not happen? Because if you take, say, take A equals to 8. Or maybe you will take A equals to 4 and B equals to 2. So what will be your A minus B? So 4 minus 2, this is 2, this is less than 3. But what about B minus A? So 2 minus 4 minus 2. Okay, this is also less than 3. Is it true? No. So as for example, you will take, say, your A is 2 and B is 9. Say. So on that case, A minus B, 2 minus 9, that will be minus 7. Yes, less than 3. But what about B minus A? 9 minus 2. This is 7. And this is not less than 3. So what do we conclude? A row B, that does not implies B row A. So that means row is not symmetric. Now we'll come to the transitivity. Is it transitive? So maybe this distance is less than 3. This distance is less than 3. But okay, so just to think about, so this is your, say, 8, this is your 6 and this is your 4. So this distance is 2. This distance is 2. But this distance is 4 and this is not less than 3. So for transitivity, what we will take? Let A equals to 8, B equals to 6 and C equals to 4 belongs to Z. Then what will be A minus B? 8 minus 6, that means 2. This is less than 3. So that means A row B, that is 8 row 6 holds. What about B minus C? 6 minus 4, 2, again less than 3. So that means B row C, B is related to C, that means 6 is related to 4. But if you take A minus C, that means 8 minus 4, 4. This is not less than 3. That implies A is not related to C. That means 8 is here not related to 4. So thus, row is not transitive on Z. Okay. So in that way you can prove this kind of problem.